Hello there and welcome to Chemcrackers. Today we are going to look at cracking chemical equilibrium. So we're going to look at reviewing chemical equilibrium using 10 multiple choice questions that you are likely to get on the Unit 1 CAPE examination. Let's go. Alright, so you're looking at question 1. And question 1 is asking you for the equilibrium constant expression for the reaction between iodine and chlorine to produce iodine trichloride. Now let's look at it. We know that the equilibrium constant is an expression which gives roughly the ratio of the concentrations of the products relative to the reactants at equilibrium. So we're going to need to have the concentration of the product. In this case, the product is ICl3. Okay, ICl3, and we're used to the stoichiometric coefficient, which is 2 over the concentration of the reactants, which are iodine and chlorine, raised to their stoichiometric coefficient. Okay, and that's 3 for chlorine. Okay, so based on that, we can see that our answer is going to be D. Okay, so just quickly go through some of the misconceptions here. Firstly, you never have a plus sign in the middle of your expression for Kc, so that's out. You also never have numbers before the concentrations. The numbers are inside the brackets or an exponent of the concentration inside the bracket. So these are out. And this one, everything is wrong with that because it doesn't have the the stoichiometric ratios there expressed in the expression for Kc. Let's go to question 2. Now question 2 has the contact process, or at least one of the stages of the contact process, the oxidation of SO2 to SO3. And the question says, what temperature and pressure conditions produce the greatest yield of SO3? Now this is an exothermic reaction, and it's also a reaction that has more molecules on the left hand side than on the right hand side. So in terms of temperature, you would want to shift to the exothermic side. That means you would want to have a lower temperature. So you're looking for low temperature. And in terms of pressure, to shift to the side with less molecules, you would need a high pressure. So you need high pressure and low temperature. So your answer there has to be B. Okay? Now I'll go to question 3. Question 3, what will happen to the position of equilibrium and the value of the equilibrium constant when the temperature is decreased in the following reaction? Now the reaction has a 1 to 1 to 2 mole ratio. It's an endothermic reaction. Okay, so we're just changing temperature. So let's look at it. Okay, so what you have to do then, okay, if we decrease the temperature, that's going to shift the equilibrium to the exothermic side. Okay, so that's going to shift it to the left, that is towards the reactants. And also, because temperature affects the value of the equilibrium constant, and Kc will be talking about the forward reaction here. If I go the other direction, I would decrease the value of Kc. So my answer here is A. Now let's look at question 4. Which statement concerning a chemical reaction at equilibrium is not correct? This is a question that comes very often on the CAPE exam, or a similar question anyway. The concentrations of reactants and products remain constant. That is okay, because remember, in dynamic equilibrium, macroscopic properties are constant, and concentration is a macroscopic property. Alright, and then B, equilibrium can be achieved starting with a mixture of reactants and products. That's true. Recall that one of the features of dynamic equilibrium is that equilibrium can be attained from either side. So you can start with reactants or products or a mixture. And C says the rate of the forward reaction equals the rate of the reverse reaction. That is true. and that is why the macroscopic properties are constant. And then D says the concentration of the products is equal to the concentration of reactants. This is not correct, and this is a common misconception among students. You have to be careful. The concentration of the products don't have to be equal. They may be, but they don't have to be equal. Um, they just have to be constant. All right. So D is incorrect. For which of the following systems would the position of equilibrium not be affected by pressure changes at constant temperature? This is question 5. Now, for this to happen, all right, for the pressure not to affect the position of equilibrium, then what has to happen is that the number of molecules on the left-hand side of the equation must be equal to the number of molecules on the right-hand side of the equation. Okay, so that occurs with B. 2 molecules on the left, 2 molecules on the right. That's the only one that's like that. Let's look at question 6. Question 6 says, consider the following equilibrium reaction in a closed container at 350 degrees Celsius. It's SO2 plus chlorine gives us SO2Cl2. The reaction is exothermic. It's a gas phase reaction. Which statement is correct? It says, A. Decreasing the pressure will increase the amount of SO2. Well, if you decrease the pressure, it will shift towards the side with more molecules, and that would be your left-hand side. The left-hand side has 2 molecules compared to 1 on the right-hand side, so A is not correct. C says increasing the temperature will increase the amount of SO2Cl2. That's not true, because if we increase the temperature, we'll shift to the endothermic side. That's the left. And catalyst has no impact on the amount of SO2Cl2 because catalysts do not affect the equilibrium position. The answer is B, decreasing the volume of the container, which means they're increasing the pressure, will increase the amount of SO2Cl2. Question 7. H2 plus I2 equal 2HI. And it says at a certain temperature, the equilibrium concentrations are in mole per dm cube, and you're given the various concentration, and they ask you what is the value of K. Alright, now Kc will be the product concentrations raised to its stoichiometric coefficient, which is 2, over the concentration of the reactants times each other raised to their stoichiometric coefficient. And the reactants are I2 and H2. It doesn't matter which order you put them in, as long as you have the right coefficients, and both of these have the coefficient of 1. And so if you put that in, that's going to be 3 squared. Concentration of HI is 3.0, and I2 is 0.3. Alright, and concentration of hydrogen is 3.0. 3.0. Alright, and so that is going to come to 9 over 0.9, which is equal to obviously 10. And so my answer is A. Let's look at question 8. Question 8 is asking for the equilibrium constant for a reverse reaction, having given you the forward reaction. Let's look at it carefully. So it says value of the equilibrium constant for this reaction, 2HI gives you H2 plus I2, is 0.2 at 440 degrees. And then it says what would be the value of the equilibrium constant for the reaction at the same temperature below. And look at this reaction. If you look at them, you see that this one is the reverse of the first reaction. Alright, so Kc for the reverse reaction is equal to 1 over Kc for the forward reaction, as long as you're at the same temperature. And so all we have to do is to say 1 over 0.2, and that gives us 5. So my answer is D. Okay, let's look at question 9. Now, question 9 has to do with the Haber process, the reaction of nitrogen with hydrogen to produce ammonia. So in this reaction, they're asking you for the value of Kc, and they're giving you information as to the amount of nitrogen and hydrogen in a mixture at the start, and how much ammonia is produced at the end of the reaction or at equilibrium. So let's just read it carefully. It says a mixture of 2 mole of nitrogen and 6 mole of hydrogen was allowed to reach equilibrium in a 1 liter vessel at a certain temperature. And then it says at equilibrium the vessel contained 0.6 mole of ammonia. Okay, so there's my reaction, my equation for my reaction. Alright, and so what you have to do is that you have to do the ice, you have to work out the initial amounts, the combining amounts, the equilibrium amounts finally, and then they use the equilibrium amounts to calculate Kc. So let's get to that. So the first thing we're going to do is that we're going to write down the initial amounts. So I'm going to use I here to denote the initial amounts. And we're told that we're starting off with 2 mole of nitrogen and 6 mole of hydrogen. So I'm going to just put 2 moles here of nitrogen, and we have 6 moles of hydrogen to start out with. We're not given any information about ammonia, so that must be non-existent in the mixture at that point, at the start. And then we're going to write C for the combining or reacting amounts, and then E for the equilibrium amounts, which we're going to use to do our calculation. I'm just going to do this table so that it's clear for you to see. Okay. Alright, so let's go back to the question, because it's okay to have the initial amounts, but we need one other data point, either a combining data point or an equilibrium amount data point to fill out this table. And so what we need is we go back to the question. It says at equilibrium the vessel contained 0.6 mole of ammonia. So equilibrium amount of ammonia was 0.6 mole. Okay, now once we have that, we can use that along with the initial amount of ammonia to work out how much combined, and then work out the rest. We started with no ammonia and we ended up with 0.6 at equilibrium, which means that we must have increased the amount of ammonia from 0 to 0.6. We must have made all of that. Alright, now the amount of products increase while reactants decrease during a reaction. So I'm just going to put negative for both of those reactants. Okay, now in terms of the combining amounts, that's going to be the same ratio as in the stoichiometric equation. Always remember that the combining or reacting amount or reacting ratio is the same as the stoichiometric or balance equation ratio. So it says here 2 moles of ammonia is formed from 1 mole of nitrogen. So if I have 0.6, then half that amount of nitrogen would have been required. So half of 0.6 is 0.3. So I know that 0.3 mole of nitrogen must have reacted. And then nitrogen to hydrogen is 1 to 3. So if this is 0.3, then this must be 3 times that amount, which is 0.9. Now we can work out the equilibrium amounts of hydrogen and nitrogen. We started with 2.0 mole of nitrogen, we lost 0.3, So we must be left with 1.7, sorry. And we started with 6 moles of hydrogen. We lost zero point 0.9, so we are left with 5.1. And so if we can just write our equilibrium expression for the Haber process, the product, which is ammonia raised to its stoichiometric coefficient, so the ammonia is raised to its coefficient, which is 2, over the concentration of nitrogen raised to its coefficient, which is 1, and times the hydrogen concentration raised to its coefficient, which is 3. And then we fit these values into that equation. So 0.6 mole of ammonia squared over 1.7 mole of nitrogen times 5.1 mole of hydrogen cubed. And this is not mole, it's actually mole per dm cubed, because the volume of the vessel is 1 dm cubed. So if you divide the mole by 1 dm cubed, you get by the same value, but the units will now be in concentration units, mole per dm cube. And so this is your answer, which corresponds to D. Let's look at the last question, question 10. Similar to the one before, but with a little twist. So here it says, initially a mixture of 0.1 mole of NO plus 0.05 mole of hydrogen and 0.1 mole of water were allowed to reach equilibrium in a 1 decimeter cube vessel. There was no nitrogen present initially. At equilibrium, the concentration of NO was found to be 0.062 mole. So these are the critical bits of information here and here, and of course your balance equation. So first of all, I'm going to rewrite the balance equation, and then we're going to do the ice and work out the expression for Kc. Right, so 2 moles of NO plus 2 moles of hydrogen gives 1 mole of nitrogen plus 2 moles of water. These are all gases. It's a gas phase reaction. So let's fill in the initial amount. So we're told that we have 0.1 mole of NO. Go ahead and put 0.1 here. We have 0.05 mole of hydrogen, which we're going to get 0.05 here. And we have no nitrogen, so that's 0. But we have 0.1 mole of water. So I'm going to go ahead and do our table, ice table. Okay. The initial amounts, then combining amounts, and then equilibrium amounts finally. Okay, now we need one more piece of information. We're given it at the end here. At equilibrium, the amount of NO was found to be 0.062. So NO was 0.062 mole at equilibrium. Now what that allows us to do is to calculate the amount of NO that actually reacted or combined in the reaction. Now it started out at 0.1 and it goes down to 0.62. So we must have lost some NO, so I'm putting a negative sign there, and that would apply to all the reactants, while the products would have increased in amount or concentration. So I started at 0.1 and I'm down to 0.62, so I would have lost the difference between the two. So 0.1 minus 0.062 would be 0.038 mole. Alright, now according to my equation up here, these reactants combine a 1 to 1 mole ratio. So that means, or 2 to 2, so that means that the same amount of hydrogen would have reacted. Okay, so I'm going to go ahead and put 0.038, and I also would form the same amount of water because they're all in a 2 to 2 to 2 ratio. And I would have formed half the amount of nitrogens, 2 to 1. So I would have been forming half of 0.038, which is 0.019. Okay, now I can work out the equilibrium concentrations for the other three materials in the mixture. Here I started at 0.05, I'm losing 0.038, so I'm ending up with 0.012 mole. I'm starting at 0, I'm gaining 0.019 mole. Okay, and I'm starting at 0.1 and I'm gaining 0.038, so I'm ending up there. I have all the equilibrium amounts. Now remember, these would be in mole, but the volume of the vessel is 1 decimeter cubed, so if I divide all of them by 1 decimeter cubed, I would now get the value, the same values, but it would now be in mole per dm cube. So I am just going to go ahead and write the expression for Kc for this reaction. Alright, so if you look at the expression for Kc, which is concentration of N2 times H2O squared over NO squared times H2 squared, and we just fit the values in here for N2, for H2O, and for NO and H2, and the answer works out to be C. Thank you for tuning in again to chemcrackers. Please share this video, like this video, make a comment, tell me what other topics you want me to cover, and see you next time.